Oh, it's not being announced, just shown. Interesting.
Okay, I will go ahead and get started. Let me welcome our speaker today, Dr. Thomas Plutz. He's a computer scientist with expertise and decades of experience in pattern recognition and machine learning. I have followed his work for quite a while because we're both interested in modeling human behavior from sensor data, and he has been working in that area in computational behavior analysis for quite some time. He's interested in making this work in the wild, so not in laboratory settings, but in everyday settings, which is just wildly noisy and complex. He is currently an associate professor of computing at the Georgia Institute of Technology in Atlanta. Before that, he was a reader at the School of Computing Science at Newcastle University in Newcastle upon Tyne in the UK. He's very active with MWIT, which is one of the conferences, journal combos in pervasive computing, and he has served as general co-chair for the Joint Conference on Pervasive and Ubiquitous Computing. He's a distinguished member of the ACM. We are grateful that he is here to talk to us today about his ideas and experiences. So I will turn it over to him and let the audience know that you can raise your hand if you have questions. He's open to questions during, but we will certainly have time for questions after the talk. So Dr. Plutz.
Wonderful. Thanks very much. Let me, the usual question, can you see my screen, my slides?
Yep, they look good.
Wonderful. And I will also open the chat, but I can see if things are happening over here. All right. Thanks very much. Thanks for the introduction, and thanks for having me. I can get all the compliments back to you, Diane. I've been following your work for a long time, and you're right, we're working in a very similar field, and it's great to be here. And Maureen, I see you as well. Good to be with you in the room as well. And we started talking about the opportunity for me to present our work to the group over here. So I discussed with Diane and Maureen a little bit, and I was informed that I want to focus a little bit more on the application side, on the deployment side of our work, and I'm trying to do that. So please just chip in whenever you think it's needed. Okay, so I want to talk about computational behavior analysis. Computational behavior analysis is the name of my lab at Georgia Tech, and also was it at Newcastle back in the UK, as Diane mentioned. And I thought long and hard about this because what I've been doing for the last 15 years is essentially activity recognition. But I believe there's more to activity recognition, specifically for the application domains I'm focusing on, which is health. And I call this digital health. And I want to basically get into a foray of what I believe computational behavior analysis is, where I see the community right now, and then jump into some examples of the work we've been doing over the past N years, and I leave N as vague as possible. All right, so what do I mean by computational behavior analysis? I want to give a first example, and I'll share a video on the next slide, and I would like you to just pay attention to the interaction that you're seeing over there. There's a bit of audio in the beginning, that's kind of important.
Aaron. Look what I got. Here we go. Ready? 1, 2, 3, go! 1, 2.
All right, so this is a typical interaction where computational behavior analysis comes into play. What we see here is an effort we've done a few years back here at Georgia Tech, where we looked into developing a screening system, a pre-screening system that shall ultimately be able to detect red flags or indicators of potential autism in kids in the age of 2 or 3 at this kind of age. So we see one individual here, the little boy, who was 2 at a time, sitting on mom's lap, and on the right-hand side you saw an examiner, an health individual who is trying to engage this little boy into a dyadic interaction. So for the boy, it's all play, as all young boys in his age to play with balls, and she's trying to do this in a very structured way. So there's a protocol, it's called Rapid ABC, which is a screener that looks specifically into behavioral signals of potential autism in there. So what she did in the beginning called the boy's name, his name is Aaron. And the first signal she was looking for is, does the boy actually respond, make eye contact with her? And the second one is this dyadic interaction. So she's rolling the ball back and forth with the boy. And there's one catch in there.
Go! 1, 2, 3, go! 1, 2, 3, go!
Right, so these are relevant signals that trained developmental psychologists look for to assess whether the person might be on the autism spectrum or not. So you also see there's a lot of technology involved in there. So the little boy is wearing some sensors, she's wearing some sensors. I'll get to this in a second. This is all because the idea of this project was to develop an automated screener that ideally could be rolled out into nurseries and kindergartens to do like a population-wide early screening for autism. That's not to cure anything or whatnot, but it's basically to identify autism much sooner than it typically is. Right now, it's at the age of 7, which is very, very late. And that's basically the idea over here. So that's one example where trained clinicians, trained psychologists in this case, are engaging with an individual, observing their behavior and specifically the behavioral signals. That's what I mean by computational behavior analysis, where we have the analysis, the computational tools to actually support that. Here's a few more examples. I'll get into details later on in this talk in there. What it boils down essentially is that we're looking at physical behaviors that are based on movements, on parts of the body, on the body in itself. And that can be agglomerated and aggregated with different temporal contexts and more spatial contexts and other kind of contexts into higher level concepts such as activities, actions, and behaviors. So that's the setting for behavior analysis, and the part computing plays here is to not only automate this, but to basically facilitate entirely new ways of looking at behavioral assessments. Behavioral assessments in clinical scenarios typically target what we call a behavioral phenotype. And a behavioral phenotype, here's a definition that we've always been used in this field, is essentially the characteristic cognitive, personality, behavioral, and psychiatric pattern that typifies a particular clinical condition. So that could be autism. We've been working in Parkinson's, in dementia, in depression, pretty much any clinical condition that is characterized by behavior, where looking at an individual's behavior would actually provide an insight into their well-being and into their health. Behavioral phenotype lives from, or is basically constituted by behavioral signals. And you had a couple of those in the videos of the little boy before. First one was this response to name calling. And the other one was this engagement into these dyadic interactions, where at some point after rolling the ball back and forth, the examiner on the right-hand side basically just stopped and looked for the boy to basically continue and fill in the gaps when he was saying go, and then she rolled the ball. And these behavioral signals, once they've been identified, they can be used in a computational or non-computational way for essentially for diagnosis and then for effective care. So that's basically the setting of where we are. And here in this plot, I've tried to illustrate basically the landscape of behavior assessments. There is the typical scenario of a behavior assessment in certain conditions. Take Parkinson's, for example, is happening in the clinic. So a patient comes in the clinic at every now and then, so not very regular intervals, and is being observed and assessed by trained individuals. So that is very reliable. So that's why on the y-axis we have two measures. Basically, we have reliability, accuracy, objectivity, etc. That's the red part, and the green part is accessibility and continuity and affordability. So in the clinic, we have very reliable behavior assessments. they're not very accessible because the patients need to go into the clinic. It's typically combined with effort and costs. On the right-hand side, we have real-life scenarios. So ideally, we would like to have deployments behavior assessments in real-life scenarios, so non-artificial, which makes the whole assessment more accessible, more natural. We wouldn't look into scripted interactions or scripted assessments. Fortunately, it's not very reliable because life is messy and there's an awful lot of confounding factors. There's an awful lot of additional activities going on. So in a way, it's a bit of a mess, and we need to strike some sort of a balance in here. So ideally, we want to be both accessible and reliable. So we want to be somewhere on the upper right, and that's hopefully where computation behavior assessment comes in here, which is somewhere at the intersection between the two, ideally somewhere in the upper right. So that's our setting. That's what I mean by computation behavior assessment. CBA, computation behavior assessment, essentially touches upon three major categories of research and of efforts. I call them capture, analyze, and deploy. Capture is essentially how do we actually get hold of those signals that are of interest, so technical signals like sensors involved, video cameras, etc., etc. Then analyze, how do we automatically analyze these kind of signals, and then deployment. What are the actual application scenarios? What are the application opportunities for these kind of CBA assessments? I will briefly touch upon the first two, capture and analyze, and primarily focus on the deployments in this talk. So let's look at capture. So here's our example from the beginning again. So we have the little boy who, of course, doesn't know what the background for this interaction is. So boys at the age of 2, they are very interested in all kinds of game playing with the ball, etc. What we do have over here is a semi-naturalistic setting where we have a lot of sensors in there. So there's wearables. So you see the boy is wearing this just slightly too big wristband. It's a bit more fitting for the examiner on the right-hand side. So these wristbands, they contain movement sensors, inertial measurement units that basically measure acceleration and orientation. They also measure electrodermal activities. So that's an effort to look into the effective states. You see a lapel microphone. So we're capturing some speech data there. There's some cameras in there. And there's many, many, many more sensors in the environment. That is the state of computation behavior analysis. So we have sensors everywhere. We have sensors on the body. We have sensors integrated into environments. Here's a bit of an overview where the field is right now. And right now, this is early 2020s. So up to now, it's come a long way. I started working in this field in about 2008, 2009. And that was when wearables became a thing, became a commodity, if you like. So you could actually go ahead and purchase them. So on the upper right, you see very accessible, very affordable reliability. Well, we're working on this, but there's a whole zoo of wearables, starting with the classical smartwatch, then we have smart glasses, we have smart shoes, smartphones. I generously count as wearables as well. So there's a whole lot of opportunities to capture movement of physically based behaviors. Upper left, cameras, probably pretty much known to everyone, have a bit of an issue with accessibility. So you would need to be in front of a camera that is typically given in a clinic, not so much in private homes, sparse, spotty, problematic in the outer world. Lower left, Diane has been working a lot in this field. That's smart homes. Smart homes have become very popular again because now they actually work and we know what to do with them. There was a big push in the 90s where engineers like myself built some just because we could, and then we didn't quite know what to do with that, and then they died down a little bit, but they're a thing now. They're commercially available. Many houses have smart doorbells, smart kitchen appliances and whatnot. Great opportunity to capture relevant behaviors. We played a little bit with integrating sensing modalities into everyday objects. That's what you see on the lower right. That was back in Newcastle, where we put IMUs into kitchen utensils in an effort to essentially collect and continuously assess kitchen activities. Newer stuff are voice-based assistants as the Alexas and the the Google Homes of the world, and also on. To summarize, capturing, I wouldn't say it's a solved problem, but there's a lot of opportunity to capture behaviors where they happen. And again, I'm talking about physical movement-based activities over here. I describe myself as an opportunistic sensing person. I'm not dogmatic or religious about a specific sensing modality. Whatever sensing modality is available and applicable and appropriate will give me the signal. There are some challenges with that one. Wearables, for example, they have to be low power. They typically don't have huge computational power, computational methods in there. But these are all challenges that can be overcome or can be addressed at least at some point. And also, you know, every single conference I just came back from the UbiCom conference, there's always some new sensing modalities there. I'm amazed about the creativity of the community. There's so much going on. So that's the first component of computational behavior assessment. Now, with all this wonderful data that we have, movement data, context data, location data, and whatnot, we need to analyze that. And the analysis of this kind of data can essentially, at the conceptual level, be broken down into what I call human activity recognition. So here's one of my most favorite examples of human activity recognition. It's football. Some call it soccer. There's also a very technocratic definition of human activity recognition. I spare you the detail. That's the Wikipedia definition. Here's my definition. What is happening and when. That is the pragmatic definition of human activity recognition. We extended this a little bit in our work, where we looked into how well is something happening, quality assessment, skill assessment. Is it changing over time, which is indicative for, especially for health conditions. Under the hood, typically we have to solve a problem like this. Here's a real-world sequence of accelerometer data, tri-axle accelerometer data worn by myself on my wrist. I forgot what I did the first 2/3 of the recording over there, but the last third right here is basically me walking. So that is one example of behavior analysis that basically starts with gait analysis and then integrates this into, for example, in routines to assess how much do people move about, where do they move about, combine it with different context factors in there. What I want to show you is how messy this whole data is. There's a lot of challenges in there, and these challenges require sophisticated signal processing and machine learning techniques. There has been a standard for a while. Again, just an overview over here. This is a typical human activity recognition pipeline where we have essentially 5 conceptual blocks. On the left-hand side, we have the raw data collection. That is a number of sensors provide us with data, which is essentially time series in multiple dimensions. Then we have to do some pre-processing, which essentially filters the data, cleans the data, normalizes data to some extent. Segmentation is essentially a hack. The analysis of these kind of behavior data is essentially a dual problem. So first we need to find out where something of interest is happening, that we call segmentation, and then afterwards we need to classify it, basically saying what is happening. Unfortunately, that's a chicken and egg problem, because we need to know what we're looking for in order to know where to look for, but we need to know where to look for in order to know what we're looking for. I think it sounds better in a classroom, but let's leave it there. We use this sliding rectangle that goes over the sensor data there, basically just to circumvent this problem, and then we look at these portions of the data in there with a machine learning backend, what you see on the right-hand side over here. Now, this is a challenging problem. Challenging problem because, as you're seeing on the lower right here again, this data is very noisy. There are ambiguities at many levels. There's ambiguities in the sensor readings in itself. These are all, to some extent, mechanical devices that sense that might get stuck, might lead to faulty sensor readings. There's calibration issues. More on the conceptual level, the activities in itself are not always very well defined. So when does walking end and when does running start? It's not usually well defined. That makes it a bit more challenging. The biggest challenge of all for developing these computational behavior assessment systems is that ground truth annotation that is typically needed for developing these systems and also for validating it is not so easy to get by. It is often not very practical to follow people around and label their data or ask them to label the data, which results very often in data sets that we can use for building these systems, for developing these systems that are very small and they're very imbalanced. On the upper right-hand side, you see a typical example is one of the benchmark data sets in the field of wearable computing, where 75%, the big green part over there, are the other activity. So these are 75% of activities that are not relevant, but could be anything. All right, so the other 25% is what we're actually interested in. That needs to be taken care of at the modeling side. And a lot has happened there. This is just a summary. So it started, of course, in the mid-2010s, early 2010s, where people realized that neural networks are a thing again. Now we call it deep learning. That's not doing the whole thing justice. There's a lot more to that, but of course, there's much more sophisticated processing pipelines now as well. It's starting with some feature engineering, where we actually did a bit of piloting work in learning these representations. And then we have on the upper right, this classical end-to-end learning. That's what we hear in the news everywhere. That's these very large deep neural networks, AI models right now. What's happening in the field right now for the last, let's say, 5-6 years is that the community realizes and embraces that we don't have an awful lot of labeled sample data or example data that can use for training our models, but we're typically not short of unlabeled data. So embracing those two facts led to a very big push on what we call self-supervised and unsupervised learning, and especially transfer learning. So that's what my lab has been doing the last 5-6 years quite a bit. I'll spare you the detail. We can go into technique details if you're interested. Now, what I really want to focus on in this talk is these deployments, these applications that we have been doing. And the whole thing is motivated by two key events in my life as a researcher. The first one was my PhD defense back in Germany, which is public in the sense that your mother-in-law could show up for a defense. And it happened to me. She was there, and a very smart woman, very smart individual. She read up on the stuff I've been doing. I've done my PhD in bioinformatics, and I passed, yay. And then afterwards, when we celebrated, she came up and asked me, well, you're a doctor now. This is great, but tell me, so how does it actually change the world now? And I was shocked a little bit that I couldn't convince this very smart woman that what I did mattered and actually made an impact. But that's a different discussion. The other discussion, and that was the first decision for me, the epiphany moment for me to move into this health field to actually have an impact. The other thing is a quote my good friend and colleague, Gregory Abaut, put in one of his talks in 2011. So I did a postdoc at Georgia Tech in 2011 with Gregory. And in one of his talks, he claimed that in 5 years, remember, that's in 2011, in 5 years, the majority of clinically relevant data will be collected in non-clinical settings. So I report my blood pressure readings to my physician because I have a device at home. So my home is a non-clinical setting. That's one example. There's many other examples where we report sensor readings and report health data from our homes. One big factor in that one is the availability of sensors. They're all there. I will not answer the question whether we're there yet, because it's a relatively vague statement. The majority could be 51%, could it be a supermajority? I don't know. What I know is that we've come a long way since 2011, and many of these kind of data, clinically relevant data, are actually collected in non-clinical settings. So that's basically where we're coming from with our deployments. We want to focus on actual clinically relevant deployment scenarios. I've put in 3 major categories here, what we've been working on the past 10 years. First one is assessing behavioral phenotypes, as I started the talk in the beginning with, where we looked into developing methods and deploying methods for different, a range of conditions. And we looked into any kind of activity, in any kind of clinical condition that is typically assessed by looking at behavior of individuals. That's autism, Parkinson, and depression. I want to talk a little bit about our work in Parkinson's back from the time in the UK. The second component is a bit unusual. That's been work we've been doing the past 5 years here at Georgia Tech, where we look into one specific behavior, one specific set of activities, and correlate this to mental well-being, and that's eating. And the third one, towards situated intervention, that is an ongoing, relatively new effort here at Georgia Tech, where we are leading one of those NSF AI centers, and we just finished the second year, where we specifically focus on population with mild and cognitive impairments. All right, the first part is on Parkinson's assessment, and all credit goes to my former PhD student, Niels Hammerner, whose PhD back in the UK was about Parkinson's assessment. Parkinson's, just as a quick summary, is a neurodegenerative condition that affects surprisingly many people. So 1% of people over 60. There's no cure for it. There's only symptomatic treatment. And symptoms are typically motor symptoms. And you can see this on the lower right. There's Michael J. Fox, actor from Back to the Future, fantastic movies, who has Parkinson's, and who's an activist in raising awareness for Parkinson and pushing research on Parkinson's. He's here on an interview with the BBC, and he's deliberately not on his medication. And you see his restless movements, his it's called dyskinetic movements. That's the part of the Parkinson. This is part of the motor symptoms. So there's tremors, there's rigidity, there's general slowness of movement, there's these involuntary movements in there. And with those kind of symptoms, quality of life is very much depending on good disease management. And disease management is essentially focusing on limiting the symptoms to a minimum. And the idea here is to look at particular states, and there's an on state and an off state. An off state is when the symptoms of Parkinson's are not well controlled. An on state is not the absence of symptoms, but it's the state when the symptoms of Parkinson's are controlled in some sense. Dyskinesia is these involuntary movements that we saw in the videos over there. And what we have here in this example is a gentleman who has Parkinson's. In the left video, you can barely see it. He needs constant support by the gentleman on the right-hand side in the left video, who is at a regular basis basically nudging him, because otherwise he would stop. And that's called freeze of gait. There's freeze of movements. It's very typical in Parkinson's. The right-hand side, the older gentleman still has a bit of an awkward gait, but he walks independently. He doesn't need the constant nudging, and that's what the medication basically does. Side effect of the medication is dyskinesia, as you've seen. And the idea of Parkinson's management is to essentially look at the symptoms over the course of a day and to optimize the time a patient would spend in the on state, minimize the off state, and ideally avoid dyskinesia. And doing that by changing medication regimes. Now, the basis for that medication regimes are doctor-to-patient interviews that in the UK, if you're on the NHS, the National Health System over there, happen once every 4 weeks. So once every 4 weeks, the patient comes into the clinic and the doctor is having a conversation with them saying like, how are you doing? And the Brits being Brits saying like, yeah, not too bad. And that's the basis for the medication. We thought we could do better. Our clinical partners told us, well, we have to do better. And if you remember, the main manifestation of Parkinson's are these motor symptoms. So there is an opportunity to actually sense motor symptoms and do something about that. Here's what we did. On the upper right-hand side, you see a small puck. It's relatively small, about like 3 or 4 centimeters long, which we integrated into a wrist-worn sensing device. And the patients wore these wrist-worn sensing devices. As they went about their daily business. So we had a study with 34 participants where we looked into at-home assessments and as a gold standard in the clinic laboratory assessment. That was basically for training the models kind of aspects in there. Important thing is 7 days monitoring for the at-home assessments, and the patients kept their state diaries, so whether they are in on, off, dyskinetic, or asleep, on an hourly basis. So there were no restrictions on what kind of activities they're engaged in. They've all the freedom they could do. It's a fairly large data set, and the hope was to essentially replicate these patient diaries, because if we could do that to some extent and to some degree of accuracy, then we could actually give them a tool that is much more accurate than this once every 4 weeks. How are you doing? Yeah, okay, it's okay. All right, we did this. We built a fairly complex machine learning system. I spare you the detail, and I'll give you the results of this study. So again, 34 participants with all the settings in there. And here's a snapshot of the data set where we have 3 participants in the columns, and for each participant 3 days. The blue line is the ground truth provided by the patients from their patient diaries, and we have the same for the lab assessment. And the model produces a probabilistic distribution, a prediction of what state we believe a patient is in: asleep, off, on, or dyskinetic. And here are the results. So it's a probabilistic model. So the more red, the more certain the system is that a patient is in a particular state. And you can see that it is following it very nicely, the actual ground truth. It actually fills in the gaps. Look at participant 1, day 1. They didn't provide annotation for what happened between midnight and about 6 o'clock in the morning, but they would be asleep, and the system very nicely predicted that. You also see participant 3, day 3, lower right, not having a great time because very often slipped into dyskinetic state. That's what we have been assessing with these body one sensors in there. Been rolled out in the UK quite a bit. We've been working with Parkinson's UK, and yes, rather successful deployment of computational behavior assessment. Here's the second deployment I want to talk about: eating. Eating and correlating automatically recognized eating behavior with mental well-being. I want to give credit to our student, or my student, Merabin Morshid, who did this work, who led this work, and he graduated end of last year. So great for him. Mental well-being. Shocking numbers: 1 in 5 American adults will have a diagnosable mental health condition in any given year. 50% of Americans will, at some point in their life, meet the criteria for a diagnosable mental health condition. Half of those people will develop conditions by the age of 14. As a mental health crisis, it's all over in the news. The NIH has dedicated programs for that. We picked this up and we looked specifically into correlating eating behaviors with well-being. And the hypothesis, or the hypothesis is basically that we can combine classic experimental tools or measurement instruments like ecological momentary assessment, so micro surveys targeted to an individual at the right time, at the right place. And we combine those to capture contextual information with passive samples. So that's where the computational behavior assessment component comes in there. And we want to use it to detect when people eat. And we can then basically, in addition to this, gather contextual data about the eating episodes, with whom were they eating, where were they eating, in what setting, and so on. And such data can then help us establish the relationship between eating behavior and mental well-being. So that's what this basic deployment is about. I'm focusing on the first 3 components in there. So there's 2 technical ones, which is the actual act of detecting whether someone is eating, broken this down into meal and snacking detection, and then the actual correlation between the eating behaviors and the well-being. We studied this using essentially 3 categories of tools: retrospective surveys, active sensing, that's the EMAs that we talked about briefly, and passive sensing. Retrospective surveys are basically used at the beginning to baseline and to calibrate the setting, and afterwards for annotation. So here's our meal detection system. It consists of a wearable device, which is a smartwatch. The idea here is that we basically have developed a system that detects eating through the proxy of hand-to-mouth gestures. It's actually hand-to-mouth movements. So no matter what utensils you use, your hands, knife and fork, chopsticks, a spoon, whatnot, you will always have the challenge to, at some point, get food into your mouth. So there's a characteristic movement involved in there. That's what we are capturing using the wearable. And the wearable then basically sends this data to the accompanying smartphone. The smartphone does all the heavy lifting with the machine learning method that basically recognizes these what we call eating moments. And once an eating moment has been recognized, it triggers an EMA, so a targeted and a situated survey, something like first a confirmation where you're eating at a certain amount of time, at a certain time, yes or no. If yes, then where were you? Are you or are you eating? Is it a certain location? What is the environment like? So the second part could have been done through an additional sensor that we do have access to on the smartphone. It's called location. But in this case, we chose to basically combine this into the EMA-based context assessment. So we deployed this in a 3-week study. We had 28 participants, college students, because the focus was on assessing and supporting the mental health of college students. And here's a summary of the results of the study. So details are, of course, in the papers in there. A takeaway message here is that we are pretty successful in recognizing automatically these larger eating episodes, the meals. That's the lunch, dinner, and breakfast, and you can see the details over here. So breakfast, a little lower, but still 90% of detection rate of a major meal is pretty decent, pretty significant. What we are not able to do is robustly detect short eating episodes. And specifically in mental health scenarios, these short eating episodes, like snacking, they are very, very important. Right? There's a lot of eating disorders that are related to overeating or to undereating. Overeating, you inhale a Snickers in like half a minute. I inhale a Snickers in half a minute. A regular eating detection system, no matter what it would be, including ourselves, would not pick this up because there's simply not enough signal. So we went ahead and extended the system, specifically targeting a snacking detection approach. Here's a definition we used for snacking. It's a self-identified sporadic eating episode and contains short bursts of chewing, and often done in conjunction with other activities and or with disruptions. So the classic example is sitting in front of the telly and eating crisps. Or you're on the way to the bus or wherever to your car and have a quick Snickers. That's what we call snacking. And that's difficult, as I mentioned before, to capture using these hand-to-mouth movements. So we went to the source quite literally, and basically looked at the movements, the muscle movements that happen during chewing. So it's a somewhat spooky video on the left. We also looked into opportunities and how we could actually capture these kind of movements. Now, eating detection with all kind of apparatuses on the face or in the clothes is not a new field. It's been studied for quite a while with impressive instrumentations. None of them actually very practical. We focused, and that happened during the onset of COVID. We focused on college students, and one observation is that they're always running around with headphones or with earbuds, and earbuds these days, like the one on the right-hand side, they not only just speakers and microphones, they also have sensors. And that's the opportunity to basically chip in here. So we basically collected the movement sensors through a accelerometer and gyroscope combination in the earbuds that very nicely actually capture those muscle movements that we see on the left over here. So we run a study with 80 participants in there whom we invited to come into the lab and bring their own snacks, so that they actually want to snack what they snack. And they had like a 60 minutes task where they were sitting on the table. They could walk around, they could do phone calls, they didn't actually restrict them in their activities, other than they were supposed to wear these earbuds. And we annotated data sets with regards to what kind of activities they were engaging in, chewing, talking, and other, and different food items, etc. And there's a machine-based pipeline that actually analyzes this kind of data. One of the key takeaways for this study was, as you can see on the right-hand side, that we are actually able to capture these short snacking events. So I gave the median, not distance, the median duration of a sporadic chewing episode of between 15 and 40 seconds, 47 seconds, much shorter than a meal. A meal, I think our assumption was like something between 10 and 15 minutes. So yes, we can actually recognize this pretty decently. It's only half the story. The generalization is not so great. So we need a little bit of personalized data. So that's why this result actually talks about personalization. So we need a little bit of injection of personalized data from every individual snacker, shall we call them, to actually make the system work for an individual. Some technical aspects, surprisingly, the microphone data didn't help as much, which was the one surprising finding over there. Accelerometers and gyroscope are the most important sensing modality over here. All right, so with that, we're getting very close to what we actually had in mind. So we now have a means of recognizing eating, both relatively long eating episodes we call meals, and snacking. Now, back to the original question, does mealtime and mealtime context correlate with the mental well-being of college students? So the objective of our work, and that's basically what Merab's dissertation is about, is to use eating as a window into well-being, a non-intrusive window. So there's not an awful lot of service to be filled out. We don't poke needles into anyone. It's mainly passive sensing and targeted micro service. So we have our tools as before: service, active sensing, and passive sensing, and ran the studies with everything that we have now, and basically looked into this correlation. We hypothesized that there is a correlation. We collected a bit of additional data about our participants. So 28 participants, 3 weeks, college students again. So this is all related to college students. We can't generalize beyond that. We had entrance and exit surveys where we tried to get an calibration about their general stress, their depression, or potential anxieties, personality types, and demographics, etc. Some exclusion criteria. And then we had the EMAs triggered, as mentioned before, through the active component, the passive sensing by the active analysis. And then basically asked for additional components that are related to their mental well-being and to the meal context. So with that, we have essentially enough information at hand that we can then use to draw conclusions and find potential correlations. The analysis is based on a combination of the demographic factors, demographic variables. As you can see, the MH equation here on the left: age, gender, education, personality, and those parameters or those measures that we automatically extract using our assessment system, our CBA system. So number of meals, number of healthy meals, deviation time of meal, and so on. So if we look at the result here, this table looks into, it's basically correlation analysis, and we have the independent variables, everything that we've measured, that I've had on an equation before, and so with whom are they eating, where are they eating, and is there any mealtime deviation? So when it's happening, what's the duration of the individual meals? And on the columns on the right hand side, we have the dependent variables, where we basically try to correlate these independent variables to parameters or variables of mental well-being. So affect components, like they are typically sensed in valence and arousal and anxiety and stress, as surveyed from them through the EMAs. So the interesting thing here is that we have a negative correlation between mealtime deviations for the major meals, breakfast and lunch, and mental well-being. So the interpretation of that one is, if you skip breakfast, you're going to be at least grumpy, and you might end up in mental well-being challenges in there. If you delay lunch, for example, same story. Positive correlation is, as you would think, not sitting on your own, not eating on your own. So having meal context with family, with friends, positively affects your mental well-being. So the summary here is that meal context and well-being can be measured and are actually correlated, and we have positive outcomes here that you should have meals with company and eat at home, negative mealtime irregularity and skipping meals. So that sounds kind of obvious, but actually it's not, because there's a bit of a chicken egg problem here again, that there might be folk wisdom that you should actually, don't eat alone and eat at home, eat at regular times, but there's no actual measurement instrument out there that would provide and support this statement. And here we go with passive sensing combined with some clever ways of active sensing through EMAs and some calibration through surveys. We can actually provide this kind of data, and that's significant for a lot of nutritionists and also for mental health research. All right, the third one is a shorter one because I just want to basically just round things up on the deployments we're looking at, and then make my way on what I have described in the abstract as, and invite everyone to look into what's the future going to be for computational behavior assessments, looking at situated interventions for people with MCI. That is one of those more recently established NSF AI centers. We've got this a couple of years ago, so we just finished the second site visit in August. So that's a relatively large consortium where we focus on designing, developing, and deploying interactive intelligent systems embedded within communities of users over extended period of times, specifically to support, first to assess and then to support adults living at home who are undergoing certain age-related cognitive declines, specifically focus on mild and cognitive impairment. So that is, as our clinical partners refer to it, is pre-dementia, where there's still an opportunity to actually do something about it, to at the very least plateau the cognitive decline. And the angle we have over here is that we're basically focusing not only on the individual with MCI, but on their entire care network. So that's why it's called caring, where the NG is the network groups. Capabilities and what we're aiming for and have been working on in the last couple of years is that we focus on personalized longitudinal models of user behavior. I want to talk a little bit about this in the next 3 minutes. We recognize and adapt to changing user abilities, etc., and we want to provide coordinated assistance through these personalized models that we have, with the ultimate goal to coordinate care across a network of people, not just the individual, but it's the individual and their entire network in there. I want to talk a little bit about the technical foundation, which is the longitudinal behavior assessments. All credit here to my senior PhD, Harish Harasamudram, who's basically leading this effort over here. Bit of shameless self-advertisement. If you are looking for an excellent faculty candidate and or postdoc or whatnot, hire him. He's on the job market for next year. Longitudinal computational behavior assessment. What are promises and challenges? So on the right-hand side, we see 3 examples that we briefly touched upon. So on the top, you've seen this little boy already. That's autism. Then in the middle, in the center, we have Parkinson's, and on the lower right, that is efforts we did back in Newcastle on dementia assessment through a sensor-equipped kitchen. All of these scenarios, all of these target applications, they allow for out-of-clinic assessments and also for personalized assessments as a basis for care and intervention. Challenges are substantial there, right? So computation requirements is one technical challenge. Ambiguity in data and annotations we talked about before, and we can basically just summarize, it's very complex in many ways. So here's our approach. The approach that targets developing and eventually deploying personalized behavior assessment models comes with challenges of computation complexity. We're working, for example, with one data set that we've been recording with the UK Biobank Consortium, where we shipped sensors, wrist-worn accelerometers to 100,000 participants and asked them to wear these sensors for 7 days each. If you do the math, that's a whopping 2,000 person years of data. So sifting through these data takes a lot of time, and there's also a lot of noise in there. Oh, also, by the way, there's exactly 0 labels for this entire data set. So here's our approach. Our approach is to take these continuous sensor readings and automatically discretize them for behavior analysis. And the discretization basically means we're translating these wriggly lines that we've seen in the beginning into a sequence of symbols. And these symbols, they're not just random, they actually mean something. And we call them atomic movement units. Harish calls them AMUs as a pun on IMUs, which took me like a year to understand this pun, but that's just me. The point here is that we are trying to extract these individual parts, motifs, you could also call them, in an unsupervised manner. So we are basically compressing or condensing the entirety of these kind of signal recordings that we have into a fixed set of, let's call them words. They could be syllables, they could be something. They are elementary units. And then we basically have a language-like representation, which has one fantastic advantage on the technical side. We can now go ahead and use something like natural language processing. Everything you hear right now in the media about large language models and all of that, in principle, is now open to this modality as well. We can also extract something like fingerprints on activities, on behaviors, and they're illustrated on the right-hand side. And that allows us to very quickly sift through large amounts of behavior data. We can query behavior data in a much more intuitive and much more directed way, rather than operating at this sensor level. We built a technical system. I spare you the detail on this one. Here's some early results on a data set based on wearables, where we can see 2 things. The first one is, if you look at these activities on the right-hand side, there's 2 more static activities, and static in quotes, which is standing and sitting, where the histogram of the activated activity units, these atomic movement units, is relatively sparse, as you would expect. If there's not much happening in the behavior or in the signal, then it should be captured by an individual unit, whatever this unit actually is. The more dynamic activities, like actual walking and running and going upstairs and downstairs, they have a somewhat significant and somewhat unique. They're relatively similar, but the difference in details actually make the difference here. Different fingerprints, and also a rather dynamic range over the entire AMUs. So that's our starting point to change the whole assessment of behaviors in a more intuitive and more accessible way. With that, I want to look a little bit into the future, and I am seeing in horror the amount of time that already has passed. So I want to be respectful of your time, and as much as it hurts, I think I'll skip the interpretability. We might want to do this offline at some point. And I rather want to look into what I believe the next steps are in this field. I've written down interpretability, computational human ethology, digital twins, and language of human behavior. Let me jump into language of human behavior, because I think that gives us a nice rounding up of where I believe we are heading and where I believe the field is going. So with what we just heard about the work we've been doing in the AI Caring Center, where we basically translate the rather technical challenge of assessing sensor data, multivariate continuous sensor data, essentially into a somewhat like a language task, a language analysis task. So that started as an endeavor, as an approach, as an effort to make things faster, to be able to sift through 2,000 years of data relatively quickly in a relatively efficient way, also in a more accessible way that we can do something like querying and not. And it turned into, into more technical approach, where we thought a little more in detail about what we're actually doing there. We're looking at a collection of sensor readings and compressing them or reducing them, projecting them onto a finite lexicon of elementary units. Those units we then recombine into larger units. Those units, those larger units, they come into a sequence, and those sequences, they add more context, they add more meaning. They could also be changing in there. So what I'm getting at is that at some point it dawned on me that what we're actually talking about is a language. So the motivation here, or the idea behind this this push, which we're at the very beginning, is to basically acknowledge human behavior is complex, and the hypothesis is that human behavior, as I've just talked in the past 50 minutes or so, essentially follows similar rules and constraints as natural language, such as English. So I've put them on here on the right-hand side, where we have the 5 common concepts in natural languages, which is phonetics, morphology, syntax, semantics, and pragmatics. Phonetics or phonology is essentially identifying these individual units that have a meaning to a human. So in natural languages such as English, this would be phonemes. We found the equivalent of phonemes already. That's the AMUs I was talking about. That's these individual atomic movement units that we've been using. Morphology is how do those phonemes actually change depending on how they're actually being used. So the classic example is you have let's say the equivalent of a phoneme. Let's say it's a cat. A morpheme, a morphology of cat would be cats. Like, you add the plural s. It's the same stem, the phoneme, but you're still adding stuff on top of that. The syntax is essentially how you actually form an expression based on these individual components in there, be it the phonemes or the morphemes in there. In natural languages, this would be a sentence. In our case, this could be something like a routine, could be a sequence of individual units in there that lead to something that is meaningful, that has more context and more abstract meaning in there. Semantics is essentially activity recognition, behavior analysis, and pragmatics is how these actually change depending on the circumstances. So we've done quite a bit of work on this one, and here's the slide that actually summarizes all of that, which I have brought up here. I want to give a brief glimpse on what we've been doing here. So here's an example that's with my current PhD student Megha Tukrao, where we look into how can we actually derive these concepts, these language-like concepts from behavior data, from sensor data. So we start again with accelerometer data. That's the squiggly line you can see over here. And if you look carefully, there's these individual dots in there. These are symbols. These are the AMUs that we've identified in our AMU learning that I was presenting earlier. So we can now go ahead and essentially provide meanings and labels, symbols to individual portions of these the sensor data. That's the moving spots. That's the equivalent of phonology, right? So that's essentially the first part here on the image on the right, the most left branch of our tree. With those, we also have morphology in there, and then we can basically now go ahead and combine sequences of those. And here's an approach that we're currently exploring, where we're looking into a tree-based analysis of the sequences of movemes or AMUs, so the equivalents of the phonemes in there, and see how we can find individual more complex units in there. And as you can imagine, so there's a few of them. That's a very hand-picked example, I'm not going to lie, but this is a very nice example. We have a longer recording that very nicely falls into 3 different, we call them phases over here. So you have the red phase, the blue phase, and the yellow phase in the plot on the bottom. This could, for example, be phases of an individual step, right? If you lift your foot and then you have like the turn points and you put your foot down, all derived automatically in a completely unsupervised way. That's the point here. So with that, I wanna leave it there. I think I've gone way over time, and I apologize for that. My defense, the calendar invite was a bit more generous. Sorry, Darian. What I try to get across for you here is my view on the world of with regards to computational behavior analysis, that I believe is the one of the foundations for next generation digital health applications, where we can use clever capturing analysis methods for analyzing human behaviors and human activities for actual real world applications that are not necessarily bound to clinical scenarios. I always end my slide with a few takeaways or take-home lessons learned, I hope. Opportunistic sensing facilities facilitates out of clinic real-world capturing of human behavior. That's where we're trying to be. So if you remember the diagram at the beginning, we want to be on the upper right, where it's reliable and accessible. In recent years, like 10, 15 years, AI and machine learning has exploded, and it gives us a wonderful tool set, if you like, that facilitates robust analysis of physical movement-based human activities. There's much more to human behavior. I'm well aware of that, but I'm focusing on behavior that can be captured through movements and physical behaviors. Real-world deployments of CBA target behavioral phenotypes of clinical conditions. That's the important thing here. That's the clinical standard, and we're tapping into right of that. And coming up next, longitudinal personalized behavior assessments for specifically not just for assessing, but basically to turn this around into something operationalizable, which is situated, tailored intervention and care. And the big push right now, and Maureen and Diane know what we're talking about, new foundation for behavior assessments through what I believe is learning the language of human behavior from multimodal observations. With that, thanks very much.
Thank you very much for your talk that had a lot of insights, a lot of ideas. Let me first see if the audience has any questions. And Kim, I see you raised your hand. Go for it.
Just clapping. Thank you.
Okay, all right, very good. Lear, you had a question?
Yes. Can you hear me?
Very well.
Okay. I guess a question in regards to your stuff at the end about learning a language of activities in terms of, first finding these atomic symbols. And I know, one of the problems with activity recognition is that a lot of people do the same activity in different ways. And that, requires tons of ground truth, and the sensor data is so noisy that almost every instance of it is different. So if you map that to more of your symbols, the atomic movement units, does that problem get easier? I mean, have you found that if you have a grammar of eating, and if you use your AMUs, that grammar is simpler and learnable compared to trying to learn it from raw sensor data?
Excellent question. I have two responses to that one. The first one is yes. The validation we did, whether the whole concept of AMUs actually has any legs, was on benchmark activity recognition tasks. And the bar for us there was, can we actually, through the discretization and this modeling through these AMUs, at the very least get to the point where we've been before with the continuous modeling? And the answer is yes, and actually we are way behind that, way beyond that. So we actually improved the activity recognition performance on benchmark data sets quite a bit. The second part is, and that's actually more interesting here. When I started working in this field, I was a bit shocked to see that the modeling of activities is essentially hoping that in one context window we fit the entire activity in there. So, and that never changes, which is fine if you think about walking, like individual steps. But if you have activities such as or actions such as setting the breakfast table, well, they all have different lengths and durations because they are complex activities that basically can be separated into much more lower level, less complex activities or movements or whatever you want to call that. And that's essentially the analogy we're doing with languages over here. If we can identify these individual phonemes, the equivalents of the phonemes, then the next step is a different modeling task to recombine them into these more complex activities that we're actually interested in. So that's one thing. The step in the middle there is the morphology part. So we have the individual units, the AMUs, and they change, of course, right? They change because there's different ways how people lift their feet in order to make steps. That depends on the physique, that depends on the general gait parameters and whatnot. And that's why we call these AMUs not the equivalent of phones, but of phonemes, right? Phonemes are these units that we can't make a distinction at the interpretation at the meaning level, not at the physical level. So that's what we're looking at. So we have already built into these AMUs this variability that still captures or still converts to the core of what makes an AMU an AMU. So, and that's a small building block, which is much smaller scale in what typically is currently modeled in activity recognition, where we have much longer time scales in there. So that also gives us the opportunity, as we do this in language, and you mentioned this, Larry, that if we have a grammar, we can recombine them according to certain rules, and those rules then basically determine what is the actual meaning on top of that. So we do have evidence that it already works better, and we have, I think, reasonable hope and reason to hope that once we introduce the other 3 or 4 concepts, or however many concepts we actually find, then we actually change the analysis in a much more intuitive way.
Great, sounds promising. Thank you.
I have a question very similar to Larry's. You mentioned that in the case of detecting eating behavior, you needed to get a little bit of personalized information for each subject. Do you envision a point at which we would be able to, for wearables specifically, to learn generalizable activities without person-specific training data?
I believe so. I'm hesitating a little bit. So my enthusiastic yes would be, look at these foundational models that are out there, starting with large language models. They are not very personalized. They are basically, they download the entire internet and build one model, and now all of a sudden it generalizes very well. The hesitation comes from the fact that I certainly hope that I'm not like the average internet user. I have my idiosyncrasies. So a ChatGPT or something would need to adapt a little bit towards me. And this little bit is the key over here, right? So there's few-shot learning. It's very big right now, that allows us to go from these very big models with minimal effort towards an actual personalization. In our field, we don't have these big models because, as I said, at some point, we were always running out of data. We don't have this large amount of data, but there's ways around this now, and that's I didn't touch upon at all. Like there's this cross-modality learning. We have the IMUtube, you know the system, where we basically can generate large amounts of data in there that ultimately will the models more generalizable. We will still at some point need to introduce some personalization. How much? That I can't answer. In the eating example, it wasn't actually all that much, right? So we had different sessions, and we basically did the personalization or personalized training by basically just feeding one session per participant in there, and that was enough. That's an order of minutes. That's basically just to compensate for the fact that our data set is too small, and the data set is not generic enough to capture for all the variations on people have in their jaws and the way they chew. Yeah.
Yeah. All right. Thank you. That's helpful. I know we're running out of time. There are a couple questions in chat, and maybe we'll make those the last ones about your experience with data augmentation for time series sensor data and multi-label learning, multitasking activity recognition.
Yeah. Right now, or?
Sure, if you have experience on either of those.
Yes. So data augmentation, that is, I had this on one slide where I briefly glanced over the analysis techniques. It was the lower right. That is basically this whole self-supervised learning what we're doing right now. I would summarize this, attribute the augmentation techniques in there as well. self-supervised learning is very, very powerful and very successful in our field. Again, because we are not short of unlabeled data, we're short of labeled data. And the augmentation, the whole thing started with GANs, generative adversarial neural networks, back in the days. I've never seen it actually really work in time series. It's great for static data. I've struggled myself a lot with GANs in our domain. However, and that's work we've been doing last 3 or 4 years, augmentation for representation learning. So that's one part of the entire machine learning challenge. How do we most cleverly represent our data and data augmentation there? For example, through mask reconstruction, through changing, adding certain transformation to the data, as we do this like in contrastive learning framework. Very popular there, very successful there. Second question, multitasking. The unsolved problem. Multitasking, okay, I'm reading the question. Oftentimes humans do multitasking. So during the activity recognition task, is it possible to encounter those multiple activities? So the task that's being referred, or the term that's being referred to in the literature is concurrent activities, recognizing of concurrent activities. There's no satisfying solution in there. So we as a community, including myself as an individual and my lab, I don't want to lie here, we typically focus on non-concurrent activities because it's easier. Let's put it the other way around. Concurrent activities is incredibly complex. So one approach could be, say like, okay, if we have 3 possible activities, then we basically build models for all possible combinations. Well, I hate to break it to you, humans engage into way more than 3 activities. So this is a combinatorial explosion where there's no end in sight. I remember a paper in the 2010s, I believe, where multiple, it was a twin hidden Markov model where 2 activity recognition models, each represented by a hidden Markov model, basically shared their state space. So it's essentially also an explosion of the complexity of the permutations there, but at the representation level. That's actually a more clever idea. I don't know where this paper went, whether people actually still use it. And that's a long way of saying, I don't have an answer to that. There is no easy answer to that, other than learning the language of human movements or activities, because then the hope is that if the granularity is small enough, then at some point, you probably will end up with like one individual component there, but it's speculation.
That's a great place in which to end, and a grand challenge for all of us in the field. So thank you very much again for your time, your insights, and we look forward to seeing what you're going to do next.
Thank you. Thanks for having me. Thanks, everyone.
Thanks. Bye.